Okay, welcome everyone to Hands-On Line Lab Education with Remote SEM. The voice you heard earlier was Renee Lindenberg, who's responsible for getting us all set up with this webinar, and we want to thank Renee for her work in getting this put together for us. Today's featured speakers will be Zachary Gray, and we have RAIN Network Partners. We'll explain what that is later on as we get further into today's webinar. A co-host today will be myself. My name is Bob Ehrmann, and Dr. Ozgur Cakmak from we're both here residing here at Penn State University. So thank you again for coming to our webinar today. Let me see if I can get control of this. Here we go. I don't have control right now, I don't think. Zach, can you advance the slide, Zach? Thank you. So the webinar today is hosted by the NAC National Resource Center. We're in National Science Foundation Advanced Technological Education Resource Center. So we thank the NSF ATE for enabling us to be able to provide this webinar for you. And we also are here at Penn State University. We're in the Center for Nanotechnology Education and Utilization, which is in the Penn State College of Engineering's Department of Engineering, Science, and Mechanics. The next slide, Zach, I don't have the control. The webinar is being recorded, and links will be available at 3 different places, nanoforme.org, cnau.psu.edu, and atcentral.net/webinars. And we'll provide those later for you in a follow-up email. A couple things about logistics for today's webinar. We'd like everyone to use the Q&A module. We're going to try to divide the universe up. If you have questions for for Zach or our RAIN network panelists or myself, you should, if you could, use the Q&A module at the bottom of the page. You'll see the Q&A there, icon there, and use that to put questions in, and we'll either be answering them written or may bring them up during a question breaks. Technical questions, issues with control, webinar controls, whatever, you can also put those in the chat window. If you want to say hi to one another, that's fine too. Use the chat window for that. All right, if we can advance. The agenda for today's webinar we're going to follow is right here. This is the introduction period, obviously. Dr. Gray is going to be talking about microscopy in the classroom. He's then going to do a live demonstration of the nanoscience instruments Phenom Desktop SEM. We're then going to go to our panel and talk about some educator experiences using remote access and how you, as the people who are attending today, can get involved. Some of you may have already. And then we'll do a quick summary. As I mentioned, this is our co-host, myself and Dr. Cakmak, and Dr. Gray will be the presenter today. He's an application scientist at Nanoscience Instruments, and he's headquartered in, he's in the Phoenix area, but I'm not sure exactly what town he's in. I want to say, I don't know. He'll have to say that when he gets up here. So, Ozgur, you want to say hi real quick?
Hi, everybody. I'm Ozgur, an assistant teaching professor at Penn State, and I'm in the field as both educator and researcher in the field of nanotechnology and nanocharacterization. Back to you, Bob.
Thank you very much. Okay, next slide here. Our panelists, since we have 4 of them, I'm just going to introduce them very quickly here, and then we'll bring them back on, and they'll introduce themselves later when we get to our panel. We got Dr. Ray Chui at Arizona State University. We got Maud Kuchera at North Carolina State University. We got Rich Hill at SUNY Erie Community College, and we got Yves Theriault at the San Diego Nanotechnology Institute, which is at the University of California, San Diego. So we got people scattered all across the country. Next slide. And now I'm going to turn it over to Dr. Gray, and I'll ask people to, our panelists, to mute their videos, if you will, and we'll give Zach the central stage. Thanks, Zach.
Awesome. Thank you very much, Bob. So, yeah, just to briefly introduce myself, my name is Zachary. Actually, Bob and Ozgur and I, we actually all go way back. So this isn't like I'm just meeting these guys for this webinar. I've worked with Bob on and off for the last decade on a variety of things. So it's quite an honor to get to work with Penn State again. I used to work for Penn State for a number of years as well. And then once I finished school, I moved across the country here to nanoscience in Phoenix. So Bob was right, it's in Phoenix. And yeah, it's going to be quite a fun little experience here. So I want to talk to everyone today about the remote access of the scanning electron microscope, along with just the scanning electron microscope in general as a technique, and why it's important, I think, for students to get this as an experience and a skill set. So to begin, real quick slide about the company. So Nanoscience Analytical and Penn State University are co-hosting this webinar. So Bob will talk a little bit more about the RAIN network later in the presentation. Just a quick slide on Nanoscience for those of you who haven't heard of Nanoscience Instruments. It's a small company. We're headquartered in Phoenix, Arizona. We have a team of scientists and engineers with a variety of different backgrounds. And essentially what the company does is we are a value-added distributor. So we provide training, support, service, applications development, so on and so forth for customers. So Nanoscience distributes instruments for larger scientific instrumentation companies. The one that many of you probably have heard of is Thermo Fisher. So we distribute one of Thermo Fisher's, or several of Thermo Fisher's desktop scanning electron microscopes. And I'm going to show you one of those microscopes today in real time. In addition to being a value-added distributor, we also have an analytical services department, which is kind of cool. So what the analytical services division does is, for people who need data but maybe don't have the capital funding to buy a piece of equipment to get the data, you can send us your sample, and then our analytical services will get you the data that you need without you actually needing to buy the instrument. You just buy the data, basically. So the company has grown fairly rapidly over the last 10 years. And it's been an exciting journey for me working with this company for the last 4+ years as well. So now let's dive into the presentation. The first thing we're going to talk about today is microscopy in the classroom, kind of as we know it. And then I'm going to actually show you scanning electron microscope live. And not only am I going to show it to you live, I'm actually going to remotely control it from my laptop, just to kind of show you how easy it is to remotely control this instrumentation. And then following the live demo, I believe we're going to have a brief Q&A break. So if you guys have any questions, Bob and Ozgur will address them during that little break there. And then we're going to segue over to our panelists who can talk about their firsthand experience with remote access, and then we'll wrap it all up. So microscopes of all types have made their way into educational environments. This is nothing new, right? So here you can just see compound light microscopes on every desk in a science lab. And these microscopes are the most common microscopes used today, and there's a lot of reasons why. So they're simple, they're low cost, they're readily available, and they're small, right? You can fit one on every desk. So this is kind of the reason why, one of the reasons why this type of microscope has become so ubiquitous in the classroom. However, there's a lot of other types of microscopes out there, and many of them could benefit the student as well. We're going to talk about one of those today, that being the scanning electron microscope. Now, a lot of these reasons that compound light microscopes are so common, if you were to use a microscope remotely, you wouldn't have to necessarily worry about some of these things, right? Like small footprints no longer a big deal if you're using the instrument remotely. The microscope could take up an entire room. Who cares if you're using it from home? Low cost as well. They're low cost because you need 20 of them. If you only need one of them and 20 different students can use it remotely, it doesn't necessarily need to be as low of a cost. Simplicity is obviously important regardless of whether you're using it hands-on or remotely. And as I'll show you today, the scanning electron microscope that we have here is very, very simple to use. So a quick slide on the traditional light microscope. This is actually an ancient photo that I took when I worked at Penn State of one of the light microscopes in the clean room at Penn State that I TA'd students on back there. So this is just your traditional light optical microscope, and it just uses photons to get an image. And because we're using photons, we're getting true color images. One of the major limitations of the optical microscope is max mag. So it's only typically on the order of a 100x objective. And as we'll see shortly, that's going to limit your applications. And the other thing with light microscopes is they have a limited depth of focus, and that's going to cause lots of blurry areas in your image if the sample has lots of different heights within your field of view. There are ways around this. Optically, you can use an optical profiler and do a scan, but then of course that's going to take longer and it's going to be a more sophisticated piece of equipment. So the reason that the optical microscope is limited is primarily because it's optical and it's using photons. So the microscope maker's rule, many of you may have seen this before or heard of this before, is you can't look at things smaller than what you're trying to look at them with. So because photons have that wavelength of 400 to 700 nanometers, and you can play a few tricks, and you can get the resolution of the optical microscope down to about 0.2 microns, but it's going to be really hard to do much better than that. So that's 200 nanometers, right? Whereas with an SEM, we're not using photons at all anymore. Now we're actually using an electron beam that's rastering back and forth over the surface to get our image, and the electron's wavelength is dependent on its energy. So we're no longer limited by that 400 to 700 nanometers. And as a result, we can get higher resolution images with SEM. And then just the final example of the microscope maker's rule would be tools like an AFM or a stylus profilometer. Now your resolution is actually limited by the end apex radius of your probe. So, you know, those are some different examples of how the microscope maker's rule applies. And if we highlight here, 400 to 700 nanometers, that's where we're going to be in that IR range. And the nanotechnology window, nanotechnology in the definition is the size and manipulation of features and objects in this 1 to 100 nanometer range. So optically, we're not going to be able to get there, but we can use optical as kind of a middleman to find the rough area we need to be, and then we can go to a technique such as SEM, and we can get down into that 10 to 100 nanometer range, or 1 to 100 nanometer range by utilizing electrons instead of photons. So the scanning electron microscope is, as I mentioned, it's now using an electron beam that's rastering across the surface, and the interactions of that electron beam with the surface are generating various signals. And depending on what type of signal we pick up, we can get different information. So if we detect the electrons that are backscattered from the surface, we're getting a backscattered electron image, or just basically an SEM image. Alternatively, X-rays are also coming off the sample. And if we detect the X-rays, now we're actually getting elemental information. I'm going to show you both of these in real time shortly. It's very easy to do this. It may sound complex, but it's actually very, very simple. We get grayscale images with large fields of view and best-in-class depth of field. This is one of the biggest benefits of the scanning electron microscope as a technology. Is anyone that's ever seen an SEM image knows it almost appears 3D because the depth of field is so large. We also get a much higher magnification on an SEM. So tabletop SEMs, and tabletop SEM basically means it sits on the top of a table, as opposed to a floor model, which is a larger SEM that, you know, might take up half a room. So tabletop SEMs, which is what I'm going to show you today, they're much smaller. This one here actually just kind of looks like a big computer tower. But these guys can still go quite high in magnification. So the one I'm going to show you today can go up to close to 300,000x. And elemental identification is also available. So elemental identification basically means you park the electron beam at a spot on your sample that you're looking at in the microscope, and it'll say, hey, this is 48% silicon and 52% nitrogen. So it'll actually break down the chemistry of your material and give you that data, which is really, really nice. So what I want to do is I've kind of briefly mentioned two different types of microscopes, and these are indeed two of the most commonly used microscopes in the field today, whether it be in academia or in industry. These are probably the two most popular types of microscopes used. because they are relatively simple and they complement each other very well. So I'm going to show you guys a series of images that were obtained with the two different types of microscopes. Optical will be on the left and scanning electron will be on the right. And the purpose of this is to allow you guys to kind of really appreciate how these microscopes differ and why an SEM is valuable relative to the traditional optical microscope. This may already be obvious, but all of these images I'm going to show you were taken at the exact same spot on the exact same sample. So this is a true apples to apples comparison of how the techniques differ. So the first image here is actually of a silicon nitride solar panel. So anyone that's driven down a highway and looked up and seen a solar panel, you probably have realized they're blue in color. And not surprisingly, you can see that optical microscope image is indeed blue, which is really nice. That's one of the strong points of an optical microscope, is that it gives you the true color of your sample, whereas the SEM is not true color. It's actually a range of grayscale values. However, you'll also notice the SEM image looks a little crisper, a little sharper, and equally important, you'll notice a little bit of blurriness on the optical image, but it's not so bad. But what's interesting about the SEM image is if you know how to interpret the image fully, you can actually get additional information that's not present on the optical image. So in SEM, we have something called Z contrast when we use our backscattered electron detector. Z contrast means brighter areas in your image correspond to higher atomic number materials. So when you look at that image on the right, you see those little white areas or those bright spots. We may not know what they are, but we know those bright spots have a higher atomic number than silicon nitride, which is the blue material, right? Silicon has an atomic number of 14 on the periodic table. Whatever those bright spots are, it's a higher Z number than 14, so it's probably some type of metal. But you can't make that same conclusion when you look at the optical image. Those bright spots, I mean, it could be metal or it could just be little chips of white paint. We don't know what it is, but on the SEM image, we can immediately say, hey, this is some type of metallic material on the surface. And then we could do EDS to further quantify that. And we can actually go the other way as well. So if you look closely at that SEM image towards the top right, you can see some darker areas, little darker gray shades. What this indicates is that there's a material on the surface that's a lower atomic number because it's a lower atomic number than silicon. So if you think of the periodic table, you think of things like carbon, 6, oxygen, 8, nitrogen, 7, organics, right? So the SEM image gives us that type of information as well. And if you try to find that same information looking at the optical image, you don't see that at all. There's no evidence that there's smudge there or dirt on the surface, whereas in the SEM, we immediately get that. And then we can take all this to the next level, as I'll show you later. We can do EDS, and we can actually confirm these materials are what we think they are based on the Z contrast. So another comparison, I mentioned earlier the best-in-class depth of field of the scanning electron microscope technology. And this is a nice illustration. So this is a small particle sitting inside of an iron mesh. And if you look at the optical image, it looks really blurry almost everywhere, except I did my best to try to focus on the top of that ball. But you see, by doing that, we're really limiting our focus plane. So right here, you can see where my mouse is. That's where we're focused. But everything up here is blurry, so we don't have any useful information. Now, if you look at the SEM image, you can see everything is simultaneously in focus. And again, this is the same exact sample, same exact location on that sample. And you can see in SEM, you can see these little smudge marks, and we now know that this is some type of organic because it's darker than the matrix, like we talked about in the last slide. And again, when you look at the optical, you're losing all of that information because you're not focused at the right spot. So what does this ultimately mean? The increased depth of field in SEM enables rapid inspection over large areas quickly because you don't need to continuously refocus and find a new position. You can simply use the SEM as a defect inspection instrument without having to change your settings constantly. Whereas optically, you would need to change your microscope, your coarse focus knob to move to the new focal point. And I've been to lots of labs that have SEMs, and they're using it just to quickly pop a sample in, drive around all over the sample, and look for things like these black dots here, because they can do it super quickly because everything is in focus simultaneously for a lot of different samples that you'll look at on this technique. Final comparison slide is, these are some tin balls. So you saw it on the last slide, and this one's even worse. The limited depth of focus of optical, right? I'm trying my best to get a focused image here, but you only have a small slice of Z that you can focus on. And here you can see, you know, I'm getting some of the smaller ones, but the bigger ones are blurry because they're out of the focal plane. SEM offers substantially higher resolution, which is what this slide's actually trying to show. So if you look at this box here, this green box towards the right-hand side of the image, I've shown that there are some fairly small particles that we're detecting with the SEM, and the optical's hanging in there. You can still see some of those particles optically within this green box, but it gives up at a certain point. So if you now look at this red box, you can see within this box, you can see in the SEM, you can see these tiny little particles, and in that same location on the optical image, they just appear to have vanished because the optical just gives up at a certain point. And I should mention, this is the max magnification of the optical microscope here that I'm showing you. So this is a 100x objective image, which is the standard max objective for optical microscopes. Whereas with the SEM, we're just kind of scratching the surface. I could zoom into this red box, you know, very, very easily and quickly, and we could zoom in even more if we would like. What I found by bringing the SEM out in the field and demoing it to prospects and training customers is a very large percentage of the work in SEM, especially in tabletop SEM. Over 90% of the work that we're doing is in this 1000x to 20,000x range. So in that range, we've noticed lots of different companies looking for things at that size scale. So we're not, you know, we're not 150,000x. We're not looking at, you know, like, 4 nanometer particles or anything crazy like that. But we're in this submicron to micron range. Lots of valuable information is found in this range. And these companies that I'm going and demoing the Phenom to, these are companies everybody on here has heard of. These are huge companies. It's not like, you know, some only specialized little tiny companies are using this technology. Lots of companies are using this. And this is the big idea here is this is all about the students getting a valuable skill set. And if a student is able to put SEM as a bullet point on their resume, if they say, hey, I have experience using an SEM, whatever SEM it may be, that's extremely helpful for them in getting employment after they finish going to college. And I speak from firsthand experience. I went through Penn State's nanoscience NMT program close to 15 years ago. I went through that program, and I got to put SEM as a bullet point on my resume saying, hey, I know how to use an SEM. And, you know, within 6 months of finishing their nanotechnology program, I got a job at a small company using SEM as part of my job as a process technician. So it really is valuable, I think, for our students to be able to say they have SEM experience, more so than most techniques. There's, as you guys know, in nanotechnology education especially, there's dozens and dozens of different pieces of equipment we teach our students. But I would honestly rank SEM at the very top of that list, along with optical. It's very important as well for students to have as skill sets for their resume. Final comparison, a lot of people may hear, oh, scanning electron microscope, and they hear, oh, electron, and they think it's complicated. It's not. So the scanning electron microscope is very easy to use. The one I'm going to show you today in particular is extremely easy to use. So on the right there is actually a picture of myself with some fourth graders, and I took the Phenom over to Mesa. So I'm here in Phoenix, and Mesa is about a 25-minute drive away. So I loaded the Phenom into a back of a van, and I drove it over there, and I set it up at the local elementary school. And I had fourth graders using the Phenom within, 10, 15 minutes of arriving and having fun with it. So it's not like you need a specialized degree or skill set or previous experience to operate this instrument. It's very, very user-friendly, as are obviously the optical microscopes as well. So finally, summary side between these two techniques, I'm going to focus on that table over there to the right. So the big thing is the imaging source is different, right? Optical uses photons and the scanning electron microscope uses electrons. But that one difference creates huge difference. My audio drops. So most notably, the one big difference is the essentially the detectors. So an optical is using an eyepiece, or your eye, and the SEM is now using like a backscattered electron detector or something like that. And on the other hand, both they have some similarities as well. So they're both very easy to use, and they don't require a dedicated operator. So if you have an SEM in your lab, you don't need to hire a special person to work on it. You know, the person in purchasing that bought the SEM could use it. It's really quite easy. And then the other thing is the SEM provides elemental contrast, whereas optical does not. And this is important because it lends to a lot of different lab content you can create for your students. There's a lot of really rich chemistry and physics behind how all of this works, which is something you could create labs around for. It doesn't have to be a nanotech lab. It could be a physics lab or a chemistry lab that you can get some cool stuff out of using SEM. So what has enabled SEM to be more ideally equipped for remote access? So in order to have a piece of instrumentation that you can use for remote access, it needs certain qualities. So things that you would like to see for remote access would be no hardware controls. So that kind of makes sense, right? If your instrument has like knobs that you need to turn to move your sample, or if your instrument has a joystick that you need to move around, then obviously that's not very well suited for remote access, because you can't, if you're not at the instrument, you can't turn the knobs on it, right? So that's one thing that you kind of need for ideal remote access. You would like to have a simplified software user interface. That's pretty obvious. Automatic functions. This is actually really important and often overlooked. So when you're doing remote access, you're going to have, naturally, there's going to be some degree of lag, right? You may be running an instrument from across the country, and you're going to notice that even a little bit today when I show you the live demo. You may notice a little bit of lag because we're broadcasting, over across the country or whatever it may be. But if you have an auto function, that's going to greatly enhance the experience. So imagine you're on a blurry surface and you're turning your mouse wheel to try to focus it, but you're also fighting lag, and you find the focal plane, but because of lag, you go past it, and that could be kind of frustrating. But if you have an autofocus function or an auto brightness function, you just click a button and the software will do its thing for a second or two, and then it's going to give you your sharp image without having that frustration of dealing with the lag. And the improved autofocus algorithm on the Phenom in particular has really, really enhanced its ability to be used remotely. And I'm going to show you guys that today as well. You want a single software package. So with SEM, I had mentioned where we not only does it get high magnification images, but we can get elemental composition information. With most microscopes, most scanning electron microscopes, those are done by different vendors. So you would have to be dealing with perhaps two monitors, or perhaps file conversions, or minimizing and maximizing windows. It would be really nice if you could have everything on one monitor and be able to do everything within one field of view and not have to know what to minimize and reopen different softwares. And that's also been incorporated into the new user interface of the Phenom that I'm going to show you today. And then, of course, easy data exporting and sharing. So those are the things we want. And the Phenom, the new UI, has incorporated all of those things. And that's what the live demonstration will hopefully prove to you guys. These things are now implemented and really well suited for remote access. Some additional attributes of the Phenom Desktop XL SEM for remote access include a large sample stage. So you can load up to 36 samples at once into the system. So here's what the sample stage looks like. It's 4 inches in X by 4 inches in Y, and we can go down, well over an inch. I believe it's about 35 millimeters in Z we have to work with. But what's important is, if you think about it, you can load up to 36 samples. So the person in the lab or the TA, they could get samples from 36 different students, and each student could prepare their own sample or whatever, and then send them all in. And then you would just need to go in one time, load their 36 samples in there, and then you could actually do remote access and allow 36 different students to run the system without even needing to go back in and exchange the samples. That's really nice. We also have high throughput. So if you did need to take the sample out and put it back in, it's going to take less than a minute or two. It's not like there's a long pump down that you need to wait for. The system was also user-friendly and user-proof. So as I showed you, fourth graders could use it. I keep picking on fourth graders. Let's say fifth graders could use it, or third graders could use it. And it's also really, really easy, and it's user-proof. This is probably even more important. So user-proof, what this means is it's impossible to break the system by clicking the wrong button. And if you're using the instrument remotely and your only option is click buttons because you're using it remotely, you can't break it. So you could set it up with your student, with your fifth grader, and turn them loose and let them click any button they want, and they're actually not going to be able to damage anything remotely, which is really, really nice. Ultra bright source. So the Phenom Desktop SEM uses a cerium hexaboride source, kind of like a next generation Lab 6 for those of you who have done SEM before. So this is a lot different than the conventional tungsten source. So here's a kind of an image of the sources and what they look like. So the tungsten source is the classic source used in SEM. And if you just look at that picture, it's a lot thinner. And as a result, the source is a lot more susceptible to minor changes in the environment. And the result to the operator is they have to do something called stigmation a lot more with a tungsten source than a cerium hexaboride source. You very rarely, maybe once or twice a year, need to do stigmation. And you can see how that is very good for remote access. If you're trying to use an SEM remotely and you have to now not only fight the focus knob, but also fight the stig X and the stig Y, it's going to make it fairly difficult. Whereas on the Phenom, because we're using cerium hexaboride, the student or operator only needs to worry about the one knob as opposed to multiple knobs. And it also provides, and as a result of that, it provides very nice image quality, even for novice users. A fourth grader who's never used an SEM in their life could walk up to the system, and if you spent a few minutes telling them what the buttons do, they could get a crystal clear image. And then a simplified software interface. I won't ramble about that too much because I'm going to show it here in a second. So here is just kind of a quick comparison of that UI. So many of you may have actually seen a Phenom Desktop SEM before. That's the classic user interface on the left that you've probably seen if you've seen one. That was developed back in 2006, and so there's over 3,000 of these systems throughout the world. So this isn't like some tiny little SEM company that just came out. It's actually the world's best-selling SEM. And what they've done, though, in 2020 is they've redesigned the entire new UI. And that's one of the reasons we're doing this webinar today is the new UI was designed with a lot of things in mind, one of them being more well-equipped for remote learning. And you can see here that the new UI on the right, and basically what we've done is it's now a 24-inch monitor as opposed to the smaller monitor there. So the image, the field of view is a lot larger. And the other big difference is the EDS is now incorporated. I mentioned earlier, you would like to have everything in one field of view. And you can see on the right-hand side there is our EDS. EDS is basically our elemental analysis, which I'll show you here in a second. So at this point, I'm going to show you guys in real time what this microscope looks like, how I can use it. I'm going to control it from the same laptop I'm projecting this PowerPoint from. And then after that, I'm going to, we're going to turn it over to Bob and Ozgur for a questions break. And then we're going to go to our panelists, and they're going to talk very, very practically about what they're doing with remote education. All right, so we're going to do a live demonstration now of the system. So what I'm going to do, hopefully you guys can all still see my screen. I'm going to go to media player here, and hopefully you can see a video view. This is a live video view of the Phenom. And I'm actually sitting at my laptop right now, so you don't see, if I was controlling the Phenom, I would obviously be using, this mouse right here. But I'm going to open that door of the Phenom from my laptop. And then what I'm going to do is I'm going to show you guys how we load the sample. So I'm going to go ahead here. I'm going to open that door. So the door should be opening. All right, come back here. So the door is open. And I'm going to show you guys how simple it is to load a sample. So here is this is the sample holder. And just note, I'm broadcasting this through TeamViewer, and we are already on a Zoom call. So there's going to be potentially a little bit of lag. But if there is some lag, just be aware that may be the reason. All right, so here's the sample holder. It's 4 inches by 4 inches. And then again, I said it goes about 35 millimeters deep. And I have a sample already loaded in here. So we mount the samples on the SEM pin stubs. And you can put anything you want on here. You can put a hair, you can put an ant, so on and so forth. And I turn this knob. And when I turn this knob, the whole tray is lowering. And then once I've lowered the sample, it's not super important how much I lower it. Once I lower the sample, I take this and I just take this entire tray and I pop it in the system. So can't get much easier than that. And then what I'm going to do is I'm going to close the door. So again, I'm going to open up. I'm running through TeamViewer here on my laptop. So I'm going to open up TeamViewer. I'm going to close that door, come back to the video view. And at this point, the sample is loaded. And then what you're going to see is an optical image pops up on the screen of our sample that I just loaded. So now I'm going to just go over here. I'm going to show you the TeamViewer view. So now you should be able to just see the UI that I'm seeing. And I'm going to go ahead and go into the SEM mode. I can click this button to go into SEM mode. There's some other buttons on here. Like there's a mag button, there's a brightness and contrast button, there's a focus button. Anyone that's seen the Phenom, the old Phenom UI, these buttons are all very similar to what they used to be. But what's new is we have these buttons over here on the right that do our EDS. So we talked about optical microscopy a little bit during the demo, and the Phenom has a built-in optical microscope. So we can still do some basic light microscopy inside of the Phenom, but then of course we can go into SEM as well. So that solar cell that I was showing you earlier, this might actually be a good one to show you. So if you guys recall that blue solar cell we looked at earlier, here it is on my, my stub. So I can actually, I'm going to go ahead and tell the system to move into SEM mode. And it's going to, so you see how long it takes. It takes a little less than 40 seconds to get into SEM. So that's really, for anyone who's done SEM before, that's fast. And the reason it's so fast is because it is a relatively small volume we're pumping out, and the system is differentially pumped as well, which helps with that pump down time. So once I get into SEM, what I'm going to do is I'm going to make a couple of moves, show you how easy it is to move around. So you can use the arrow keys on your keyboard, or I can just click with the mouse. So you see when I get in there, it automatically, it'll help us do an autofocus. And then I'm clicking on the screen. And as I click, whatever location I click is where it's going to center our field of view. So, okay. You should be able to see me move it around here. And I'm zooming in. So I click on this microscope button here, and then that's going to allow me to zoom in. So pretty straightforward. Yeah, and again, if there is any lag, I apologize. I know, like I said, I'm trying to show you this remotely through TeamViewer, but my goal is that you guys can see the ease of use of the system. So essentially, we have three knobs down here. We have our magnification. So if I turn my mouse wheel, I execute the magnification. I have brightness and contrast, and then I have as well, I have this focus button. And the little letter A on the button stands for auto. And you can turn that on and off. So if you would prefer students get the experience of focusing manually, you could certainly do that. I could right click this and I could say, okay, let's go to manual contrast, or let's go to, you know, autofocus, or I could say I'd rather go to manual focus, or I want the breakout box that many of you have seen in SEM before. Those options are all there as well. And then I'm going to show you the EDS real quick. Obviously, if you wanted to save a picture, you just click the camera button and it'll save the picture. So for EDS, if I click this little spectrum button right here, that's actually going to allow us to do EDS. So wait for it to respond. We have our EDS now, and then I can click this little plus sign, and then it's going to pull our image over, and then I'll show you what an EDS map looks like. So I draw a box anywhere I want within the image, and it's going to spatially resolve the different materials present in our field of view. And this is what we were talking about earlier. The SEM actually has the ability to color code the sample, and I'm looking at it on a laptop here, and it's not caught up yet. I'm looking at it on the Phenom, and it's already almost there. It just caught up. So you can see here, we have silicon, we have silver, we have carbon. This is what EDS mapping does. Each pixel in the image, the brighter the color of the pixel, the higher the concentration of the material at that pixel. So that's EDS mapping. Really useful, really cool. And then I can Control A and I can overlay this so you have everything at once. You can change the colors of these things, so on and so forth. So that's, in a nutshell, that's the Phenom. And then if I wanted to go back to the image view, it says, hey, this is locked because you're doing elemental analysis. And then I could say, okay, I get the idea, I have enough, and then I could stop it. I could go back to the live microscope view. I could move to another sample. That's the final thing I want to show you on here, and then I'm going to turn it over to Bob for Q&A.
I'm going to talk about the who the panelists are. They're members of the RAIN network, and the panelists, if they could come on, put their pictures up. I'm going to stop sharing in a second. They're members of the RAIN network, which actually has sites from coast to coast, from the West Coast to the East Coast. In this example here, we have people from Arizona, from San Diego, from upstate New York, and from North Carolina, representing our RAIN network providers. And you can actually do remote access from your classrooms wherever you are, just by going to our website, which you see here is www.nano4me.org/remote access. And you can all do that at any time. There's an easy fill out the request form and say what instrument you want to look at. It's not just SEM. There we have 48 different instruments available, both fabrication and characterization equipment. By far, the one that is the most utilized is the SEM. It's a very high percentage of our usage. So I just wanted to put that in there, and I'm going to now actually talk to our panelists here and let them spend a couple minutes about their experiences utilizing electron or remote access, either SEM or other instruments. And our panelists are Yves Theriault from UCSD, as I mentioned earlier, Rich Hill from upstate New York, SUNY Erie, which is in Williamsville, New York, Mochichara at North Carolina State University, or the RTNN, and Ray Chewy at ASU. And I'm going to start with Ray, and I'm going to stop sharing this here and let the panelists come up on the screen. And Ray, why don't you tell us a little bit about your experiences utilizing remote access, if you will.
Thank you, Bob. Hello, everybody. My name is Ray Choi, and I am with Arizona State University in an organization called the Nanotechnology Collaborative Infrastructure Southwest. Now, that's a mouthful, so we usually just go by NCI Southwest. And this organization is one of 16 sites of the National Nanotechnology Coordinated Infrastructure. That's another mouthful. But basically, it's a network that supports both the research and development of nanoscale science and technology, as well as workforce development for this particular field. And two of my fellow panelists from other sites within this national network, and later on you will hear about their programs. But as far as the NCI Southwest is concerned, we have been part of the RAIN network for, I think, 4 or 5 years now. And we've been doing remote access to our SEM during that time. We used a desktop SEM primarily for education and outreach, though we do use it a little bit once in a while for research also. And by the way, our SEM is an earlier version of the Phenom SEM that Dr. Gray has been telling you about just now. And so it has some of the features that you have seen. Now, in our remote sessions, we just use a Zoom link. So it's basically you don't need any kind of specialized software. And in the case of education, we have used our SEM remotely for doing labs for both community college classes as well as university classes. For outreach, we have conducted sessions with a lot of schools ranging from 4th, 5th grade all the way up through 2-year community colleges. We've also done a lot of outreach to the general public. Every year, Arizona State University has an open house, and we do remote sessions there. And also annually, our city has a STEM fair called Geeks Night Out, very unusual name. And at those events, you really get attendees from, 5 years old all the way up to grandparents. So we reach out very broadly to the public to disseminate information about nanotechnology. For outreach events, our experience have told us that it's kind of important to have the right kind of samples and make the experience relevant to the audience. For a younger audience, fourth graders, for example, bugs, insects of any kind are always a big hit. The kids really love those. The late middle school, early high school students are sometimes a little bit of a challenge, tougher to engage. Some of them have been reluctantly asked by the teacher, "Thou shalt attend this session." And at first they're not that interested. Some of them anyway, some are very, very engaged. But sometimes the light bulb just goes on and all of a sudden everything sounds more interesting. Just an example. One time I was doing a remote SEM session with a group of, I think they're mixture of 8 to 9 graders. Many of them did not seem to be very engaged. And one student suddenly asked, "Is that what they do in CSI, the TV show?" And I said, "Oh, exactly. Every crime lab in the world has at least one of these instruments." And then all of a sudden things clicked and the enthusiasm level definitely picked up after that. So that was just an example of being relevant to the audience. So in the interest of time, I'll wrap up. So just want to remind everybody that providing remote access to these instruments is a great resource for a wide range of audiences. And I strongly encourage you, particularly those of you that are educators, to check out by visiting the RAIN Network website. And with that, I'll wrap up and say thank you.
Thank you, Ray. Great job. Thanks for the summary of your work there. I'd like to now turn the mic over to Rich Hill to talk about some of the experiences that he's done, his work in upstate New York.
Thanks, Bob. So, yeah, I'm up here in upstate New York where it's nice and 73 degrees today, which is unusual, but happy to have it. So what we do is we have a nanotechnology program here, and I've discovered a way to use our SEM as sort of like a recruiting tool. We get high schools that come here that tour our facilities, and I'll bring them down to the clean room and I'll show them from the outside through our windows what the clean room looks like and some of the tools inside of it. And I'll usually put the SEM up remotely in the classroom that I have them in, and I'll talk to them and I'll put things up there. I'll zoom in, zoom out, and try to get them engaged on what they see on the screen and how close we can get and things like that. So they try to pique their interest and maybe want to come and take our program. I've been working with the RAIN for like about 7 years now, doing sessions. We also use our tools sometimes to help out at webinars. Sometimes I'll do an SEM session with a group of people on a webinar. We'll do some breakout sessions and we'll show them how it works and give them a chance to even try it. And that's pretty much how it goes over here at our end right now. So I'll go ahead and hand that off to someone else.
Thank you very much. You guys have been a great partner, a RAIN partner, and very active and always willing to do RAIN sessions for us. So we really appreciate it. Now I'm going to ask Eve the same question about his work at UCSD and his work in Southern California.
Sure, thank you. So I'm Yves Thériault, and I am from the San Diego Nanotechnology Infrastructure, which is a part of UC San Diego. And one thing I have to say is that we reach, about 3,000 students so far. And one thing is that 100% we get fascination from all the students. There's never, a student in the back of the class that looks like board. It is really, opening, I believe, brain zones. When you can see matter at the nanoscale, microscale, it really expand, your mental ability, I believe. The other thing that is nice for the kids, of course, we have provided session, elementary, middle school, high school, community colleges. The fact that they can control the SEM, of course, is very engaging, very threatening. But also what is nice in the process is that they see what is possible today, right? Being able from your own class or sometimes at home in the COVID-19 area, to be able to control real time an SEM that is located at UC San Diego at the click of a mouse, it's pretty fantastic. One thing I have to say, if you're a STEM teacher, I would strongly suggest that you proceed at least to an SEM session with your students. The fact that they can see, structure, matter at the nanoscale, really open, as I said, brain zones, make them understand why you could apply nanotechnology to solve so many problems in so many fields of science. And, eventually, as their mind mature, understand the concept, for example, of convergent science. So I will stop to this. I would say, if you're interested in an SEM session, we're not the only providers, but we're one of them. And you can basically use the RAIN network link, and we'll be more happy to help you.
Thanks, Yves. And if you act before midnight tonight, you get the Ginsu knives too, right?
That's correct.
Okay. And our last panelist is Maud. And Maud, if you can kind of tell us what's going on in North Carolina.
Yeah, sure thing. So I'll try to be brief so we can get to some questions. My name is Maud again. I'm the Associate Director of the Research Triangle Nanotechnology Network, which is in North Carolina. It's a partnership between NC State, Duke, and UNC. And so we do offer remote sessions, just as all of us are talking about, but I wanted to plug our program and let you guys know about some resources that are pre-recorded online right now. So back in March, when the pandemic hit and we were all staying at home, we started a program called Takeout Science. And this was, we were playing on the fact that all the restaurants were offering takeout instead of dine-in options. And so one of our staff members, Holly Letty, who I'm really going to give a shout out to now because she really spearheaded this, she brought one of our desktop SEMs. It's a Hitachi, not a Phenom. So sorry, Zach. So anyways, she brought it home and put it in her guest bedroom, and she started broadcasting live once a week sessions on YouTube with our SEM. And so we now have a library of a lot of different SEM sessions available on our website and through our website. They're on YouTube, so they're easily accessible. The first episode has been subtitled in Spanish, if that is of interest to anyone, and we're working to do that for more of our sessions. Each week is themed differently, and we really capitalized on some of the trends that were going on during the pandemic. So one of our episodes looked at toilet paper and other kinds of paper. One of ours looked at textiles and why different types of materials may be better suited for making masks to prevent viral particle spread. And then we even, when Tiger King was booming and one of those shows that everybody was watching, we reached out to one of our local organizations, Carolina Tiger Rescue, to get some hairs from big cats so that we could look at them. And we brought on a guest from that conservation organization to talk more about how to protect our wildlife. So again, I just want to be brief. I'll put the link to our shows online, but if you're interested in looking at anything, we're continuing that program. And if you have ideas about a future show, it's not weekly anymore, but we're still doing it pretty bi-monthly. So we'd love to hear from any educators about what would be of interest to them. And all of them are live and then online afterwards.
Thank you, Maud. Thank you very much. Appreciate it. So I'm now going to open it up for questions. There were some questions that were there. Dr. Cakmak, do you have any questions you would like to ask either Zach or any of the panelists at this point?
Definitely. So I have some questions here, especially for you, Zach. And The panelists also contributed to some of the answers, so I would like to emphasize their answers in the Q&A part as well. But Zach, you were talking about the lower costs and emphasizing the low cost, especially for the optical microscopes, and the lower costs for the SEMs. What would you say about, like, when you say lower costs for the SEMs in general, just like to give a ballpark, an idea?
Yeah, sure. Actually, as an app scientist, they pay me to not know the price of things. They don't want me to know any of the prices. I'm supposed to be the trustworthy scientist. But from working with the sales guys over the last 4 or 5 years, I have the ballparks for sure. So you can get started, well under 100K for a basic model, just like imaging only. And then depending, so, maybe, don't quote me on this, but, 60, 70K is probably a reasonable entry point for a base system. And then, depending on the bells and whistles and the stage you want, you can get, well over 150K. So a pretty wide range, but a fully loaded system, I don't think you're ever going to break 200K on a tabletop. Whereas on a floor model, you may be looking at close to $500,000. So we're not anywhere near there.
Right. So, and of course, it depends on the attached detectors and the other auxiliary items, right? So the one that we just remotely did, that one had the EDS, the secondary electron, and also the backscattered one, right? Or
correct. I didn't show you all of them due to time, and I apologize. Our Wi-Fi here in the lab actually cut out. That was the reason for our technical difficulties. It's kind of ironic. Had nothing to do with Zoom or anything. It was just our Wi-Fi decided to pick up at a not good time. But yeah, so the system in the lab has EDS, has SED, it has backscatter. So backscatter is the default detector on the Phenom. That's something a lot of people don't realize is most SEMs, the default detector is the secondary detector. On the Phenom, it's actually the backscatter detector. So that doesn't cost any extra. So yeah, that system, you'd probably be looking at maybe 120, 130K in that range would be my guess.
Right. And I also saw that you just put it on a desk, and you didn't really need a anti-vibration table, just like Ray was also telling in the Q&A part. But what would you say about the magnification? Like, when do you think it would be really problematic when it comes to vibrations in terms of the magnification level?
Yeah, really, you can do a good job. The system, generally, you don't go above 200,000x regardless. And I would say 99% of the Phenoms out there in the field do not have a special isolation table. It just doesn't require it, because on this system, when things vibrate, like when the source vibrates and the table vibrates, the way they're mechanically coupled, they're all vibrating in the same dimension. And as a result of that, the system is very insensitive to vibration. So when you look at the price estimate, you don't need to add on the extra cost for a special table. You literally can install these about anywhere and get the same performance. To give you an example, I set one up on our sales guy's kitchen table, and it performed the same as the one that's set up here in the lab.
Right. And people were interested in the compactness of your system. They were asking, like, where's the vacuum tool? Where's the vacuum pump in there?
Yeah, let me see if I can share my screen here. Let me show you guys real quick. So I'm sharing my screen again. Can you guys all see that? Okay, cool. So if you look, I'm going to move this camera down here for a second. And I got to plug it in. I'll show you guys where the pump is. So it's just a small red diaphragm pump. So it's a little mechanical backing pump. So I'm going to go ahead and
around, like, what torr level does it pump it down to?
What torr level?
Yeah.
So we're working at the -7 range at the source, and then at the imaging environment, we're typically at about 1 Pascal. So trying to get this camera to work. Oh, maybe it won't work, but yeah. So 60 pascals in the imaging environment to about 1 Pascal for a high vacuum mode is the rough vacuum levels.
Gotcha. So what would you say about the shortly maintenance of this model? Like, is it easy to
Yeah,
maintain?
there's no maintenance. So basically, no maintenance until you need to replace the source, right? Every SEM has a source with a finite lifetime.
Mm-hmm.
However, the source on this system has a 1,500 hour plus lifetime. So generally, this is probably the most common question that comes up actually when we're showing people the Phenom is the maintenance. And it's plug and play for 1,500 plus hours. And then after 1,500 plus hours, a service guy can come help you out and replace your source. So if you think about 1,500 hours, that's several years probably before, if you're using it a few hours a day, before you actually need to worry about any maintenance. Whereas like with the tungsten source, those typically will die in 50 to 150 hours. So it's a lot more frequent for the maintenance. So that's another reason it's well equipped for remote access is you're never going to have a catastrophic failure where the system just blacks out because the source burnt out. Cerium hexaboride doesn't black out. It'll slowly dull. So yeah, maintenance, maybe every 2 to 3 years, depending on how much you're using it, or less if you don't use it as much.
I guess one of the attendees were interested in like getting some tilted images about maybe like a cross-sectional image. Do you have like a Phenom model that also supplies those kind of rotational stage? Yep.
Yeah, we do. So there's two options for tilting things, right? So one option is, as you may know, Ozgur and anyone else on the call, one way you can get cross sections in SEM is just by using a special stub with a 90-degree cut in it. You can mount your sample on the cut. Yep. That's probably the most common thing people do. But if you wanted to take it to the next level and you actually wanted to be able to tilt your sample inside of the SEM, we have a eccentric sample holder that can tilt the sample eccentrically up to 90 degrees. And a eccentric tilt just means when you tilt your sample, it will refine the position and the focal plane for you. So it's actually really easy to use. But it's not free.
Right. And then we've seen that you were using TeamViewer. So would they also be using the TeamViewer if they had an account themselves? Like, what would you say about the remote access imaging?
Yeah, TeamViewer is one option, in addition to TeamViewer. So, right now I'm using TeamViewer, but I'll show you here. We use TeamViewer here at Nanoscience, and we can TeamViewer into our customers' instruments. So here I have TeamViewer, and you can see all of the different phenoms throughout Nanoscience. And this one here is the one that's in the lab that I'm working on right now. But you don't have to use TeamViewer, right? You could use, so here's the image, and you could use TeamViewer, you could use Zoom. TeamViewer is just one option, right? So I'm moving around now on my laptop. You can see the lag's a lot better now because our Wi-Fi is not broken anymore. But yeah, TeamViewer is just one option. You don't have to use TeamViewer.
Oh, thank you very much. So we couldn't answer all of the questions for the interest of time, but we'll try to get back to you with answers over emails, I believe. Yep. Thank you again, Zach. Yep.
Yeah, well, thanks everybody.
Thank you, Zach. I am going to now, let's see, I'm going to share my screen here and show you. First, I want to thank the panelists here and Zach for their attendance today. We really appreciate it. Sorry we went a little over. We had some technical difficulties. That happens in a live situation. Our president of the university had to do a webinar today that was scheduled a couple of weeks ago because his Wi-Fi went out at his house. So that happens. That's what happens at this time in the day. I want to again thank Zach especially, but also our panelists from the RAIN Network. We really appreciate your participation, and we hope you will take advantage of the RAIN Network. I know that Renee put into the chat box the www.nano4me.org/remote access. Please take advantage of that for your bringing it into your classroom or just for your usage. I want to let you know about the next NAC webinar, which will happen in January, January 28th, and it's a really exciting webinar. Dr. Saptarshi Das is going to be talking about biomimetic sensing and computing. He's in the 2DCC area here at Penn State. He's actually an ESM professor here at Penn State. I'm really excited to see that webinar in January. We will have 2 more webinars after that in the spring, roughly 6 weeks apart from there. So you can count on some more webinars coming up. So I hope some of you will attend that webinar. And also, and then I also wanted to thank you for attending and let you know that you will be getting a survey, and we really do appreciate it if you will fill that survey out. Once the webinar ends, you will get that. And again, we will be posting this webinar on 3 different sites here, and we'll remind you of that in the email. So thank you again, and this officially concludes today's webinar. Thank you.